Good evening, everyone, and a very warm welcome to this seminar. Today, we have with us Professor R. Venkatesh Babu. He is a professor at Department of Computational and Data Sciences, IISc Bangalore. His research interests include computer vision and deep learning. He and his lab mates have published multiple papers in the top venues like CVPR, ECCV, NeurIPS, ICML, AAAI, etc. He has published around 60 A-star publications in the last 5 years. He is a recipient of SERB Star 2020 and Sathish Dhawan Young Engineers Award 2019. He has served as a program chair of the AIML-Systems 2023 conferences and is also an editor for pattern recognition and area editor for CVIU journals. He has also served as an area chair for conferences like CVPR, AAAI, NeurIPS, etc. So I'd like to thank Professor Venkatesh sir for being here with us. We are all obliged and looking forward for your talk. Over to you, sir.
Thanks, Pooja. Thanks for the nice introduction. So,
Yes, sir.
I will, maybe I will stop my video because the bandwidth is kind of limited in my office. Okay. So,
Yes, sir.
um, thanks for inviting me to give a talk to women in computer science at IIT Madras. Mm, so, I just thought of covering what we are working on for the past 7 or 8 years in how to make our model robust, the deep models, which are very popular now, right? I'm going to show basically, yeah, deep has played a huge role in many of the applications, right? Not only in computer vision, take any other domain, right? Text and audio, whatever it is, it has played a huge, it has changed the entire research landscape for the past 12 years or so after the publication of AlexNet in 2012 at NeurIPS. Okay, so the agenda is like this. You see my screen, right?
It's only the first screen, sir. The
Oh, okay, right, sir.
now it's there. Organization.
Okay. So yeah, I just want to just quickly go through how deep has changed our research landscape. Okay, and things have changed very rapidly in the last 10 years. Okay, and then I want to touch upon how we are betting so much on these deep models, how reliable they are, how robust they are, and I'm going to show how what is. I just want to compare this deep models with our human perception. And I will also tell you how to craft this kind of attack if you want to attack a deep model, how to do this. Okay? And yeah, this is the first 2 or 3 parts. We will take almost 1 hour for me to cover. So nowadays, yeah, autonomous driving is everybody's dream, right? So we just don't want any driver to drive through, right? And we need not even go to the driving school painfully, right? Uh, and then trying to get a license to a driving on those things. If you can drive on its own, so this is one of the nicest applications, right? So thanks to the deep advancement, deep vision, that we have come so far, right? So this is actually a reality in many of the U.S. cities. Okay, so you go to San Francisco or Arizona, the kind of places. There are a couple of cities where you can get a ride. You can call the cab and Waymo cab. It comes to you, and then you can take a ride where you want to go. It will drop you there. Okay, right. So it is doing really fantastic now. So now they are actually trying to make these go beyond all these things, and even the trucks they wanted to drive automatically, right? And the other one is the medicine and healthcare. There are so many things that are happening. So vision has played a very crucial role in analyzing the health. Okay, given the various imaging modalities that is coming out of the healthcare, and there are many algorithms that are available now to help the doctors to assess the disease very quickly and give appropriate treatment. Okay, and similarly, if you take the games, yeah, reinforcement learning is doing wonders there. It can beat all human champions, and then yeah, computer wins always in these kind of games. And generative modeling, which is again a hot topic now. So just by giving the text query, you can generate so many images, and yeah, these phases are generated by this style gun, which came out of NVIDIA in 2018, right? So nowadays you can generate very realistic images. If I give the image, you can't even say whether it's a photograph or a deep fake. So that's why deep fake is going to be a major issue in the coming days. Okay, it's going to be very hard for us to differentiate these two, right? And there are other nice, cool applications like style transfer, where you can change the horse to a zebra, and yeah, even you can make any celebrities to say whatever you want to say, right? And you can give them expressions as you wish. All those things can be done now. So this is also kind of very related to deepfake kind of, right? If somebody is generating a video like this and then putting it on internet, yeah, it's going to be a very difficult situation. And there are some this neural radiance field which came out in 2020 SECV. So now we are able to capture the entire 3D scene in a neural network. Okay, and it's very efficient. It's very in the compression point of view, it's quite efficient, and it gives you a very nice 3D visualization. Okay. Also, yeah, the text to image generative models are very popular. DALI 3 has come now. Okay, so you just give the prompt. Okay, seagull attacking a man holding a stack of pancakes. You get very realistic, wonderful images. So, yeah. So similarly, yeah, stable diffusion is the open version of this DALI, right? Most of you know. So again, stable diffusion is available for download. You can play with it. A scientist performing an explosive experiment, and then there's one of the nice ones, Renaissance art of Keanu Reeves. You can see it keeps the identity as it is, and then kind of gives you the nice style that you asked for. And nowadays, yeah, it can do much more than all these things. So DALI 3 has come, and it's kind of previously, yeah, it was ignoring a couple of words, so many objects don't turn up. Whereas in DALI 3, they assure you that all these words are taken into account and they create the image that is 100% reflective of your prompt. Okay. So, so, yeah, prompt engineering is getting another into again another interesting topic where people know how to give the prompt to get extract what kind of image they want. Similarly, yeah, not only images, now people are generating videos just by giving the query. A boy is running in the sunflower field in sunshine. Yeah. So you have to give this go to Google, give this English to Chinese and get the Chinese text, corresponding text, and then feed to Cog video, it will work because this is trained by China. Okay. So you have to give the input in Chinese. Okay. So the ultimate objective is going to be something like this. Can I give him a movie script, and then can the AI make the movie for us, given the characters who should play what role? Okay. I think that is going to be the ultimate realization. So also people are looking at now, yeah, 2D is done. Now can we go beyond 2D and then synthesize 3D models, right? From 2D. That's very interesting. So, given the text prompt, now we are in a situation where we can create a 3D model, okay, of that. from the 2D input, basically. It's trained on 2D, but yeah, we wanted to get the 3D. So yeah, it has penetrated everywhere, right? Robotics, we take audio, NLP. So all our chat GPT kind of thing came out of NLP. In finance also it's playing a huge role, all the big models. Now, having said all these things, the deep model has done so much in the last 10 years, and it's doing very well even now. Okay, look at the number of papers that are getting submitted to top venues like CVPR. So this year it has crossed 10,000, more than 11,500 submissions this year alone. So just 10 years back, this was 1/10 of the submission. 1,200 papers were submitted. Usually 300, 400 papers are getting selected. Nowadays, it is more than 10,000 papers submitted, more than 3,000 papers getting accepted. So that is the scale at which these things are progressing. Every day you get 30, 40 to 50 papers in archive, in computer vision, in machine learning, and different kinds of areas. Okay. Right. So having said the wonderful things about deep models, now we want to analyze how robust are these deep networks, right? Because the ultimate objective of computer vision is to mimic the visual perception of human being. Okay. So when we see things, we understand how we understand. In the same way, we want the robot also to understand the scene, right? So, but on the contrary, you are seeing there is quite a few news that are coming out that you can see these autonomous driving vehicles met with some accidents. So at least once in a month, you keep seeing some of these incidents that are happening. Okay, why? What happens? These models are trained with millions of videos. Even then, why it fails in this kind of circumstances, right? So so this is another plot which shows the kind of error rate, how the error rate fell for ImageNet kind of a data set, where you have 1,000-way classification and you have 1.2 million images for training. And you can, this challenge started from 2010 from Stanford, and these are the error rates, and AlexNet came in 2012. It has showed some 16% error rate, and now we are much below, around 2.5% error rate. Okay, whereas human error rate is more than that. Okay. So, since the error rate is much bigger, then is it superior than human being? That's what many people are thinking. Yeah, deep models are much better than human beings. So this experiment shows it's the other way. It's not this case. So ICLR 17 work, rethinking generalization. What they did is they took uh, part of the training data set and then they shuffle the labels. Okay, so I will change banana to dog and tree to a dog, or a dog to a tree, something like this, randomly, irrelevant classes. So I will change this 20%, 40%, up to 100% of the time, and then try to find accuracy for training data as well as the test data. For example, if you look at this, the blue line, this is for the training accuracy, okay, which we are shuffling actually. Whereas the test set is not shuffled, it's a proper set, and we are measuring the accuracy on the test set. So as the shuffling increases, the test performance goes down, 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 close to the by chance accuracy, about 10%. Okay. Whereas this training accuracy remained all the time 100%, which means what does it do? So whatever you shuffle the label, I don't care. I'm just going to memorize this image as this label. That kind of a memorization. That is right. So people now we know very clearly these deep models memorize a lot. Okay, so that's why you are seeing such a huge gap. Okay, so training sets are being memorized. Okay, so this memorization kind of a goes against the generalization of the model. So if you look at this particular manifold, okay, what we think is on the left hand side, what actually happens is shown in the right hand side. So what you're thinking here, okay, you have a very nice manifold, all these are partitioned into various classes. Now, whenever I sample from these manifold and then give it to my model, it will nicely predict correct class. Okay, but actually, all our models are limited by the amount of data that it sees, right? So you are looking at this side, you can see there is a lot of gray area that you are. So which means this area, though it is looking small, actually this huge amount of such area exists. And we never got a sample from these kind of locations for trained our model. So whenever the new test sample comes out of this gray area, this model does not know what to do. So it will just randomly fire some class, okay, which is most often incorrect class. Okay. So this is, if you look at in a 1D case where we can easily realize I have a data and I can nicely fit uh, a regression model for this data, given data, right? So it perfectly works whenever the data comes within this particular window. And when the new data comes outside this window, which was not used for modeling, then we don't know how the model is going to behave, right? That's never seen, right? So that particular region, the region left and right, they were not supported by this model, right? I also want to show how the human perception differs from the machine perception. Okay? For example, if I show this image, I ask you what is there in the image, most of you will be confused. You can't guess what is there in the image. Okay, but if I give this image to a model, right, it has no issues in predicting this as a dog. I don't know where are the dog features for this image, but it could predict this as a dog. Because this image is actually constructed from this particular image, right? You take the patches and then scramble these patches in random fashion and then create a new image. Okay. And this also shows the CNNs actually learns from the local patches the information. So since it is local patch informations are intact, so it has the dog queue is kind of getting amplified and then it detects as a dog. Okay. And we cannot say this as a meaningful entity, right? Okay. Whereas this is another image, we have no issues in understanding this particular image, right? If I ask anyone, you can say this is a car. You can also say it's a sports car. What kind of a car it is, right? But the same thing, the model predicts as a toaster. Okay, right. So we'll be wondering what happened to the model, why it is predicting as a toaster. Okay, so how this image is generated is we just took the original image, which is here, and added some adversarial perturbation. So these are scaled to show the adversarial perturbation. These perturbations are very mild. Okay, the range of the perturbation is plus or minus 8 by 255. That's all, right? So it's less than how much percentage? Less than 2% of your image size, the image range. Okay. So if you add such a mild noise to your left image, you hardly see any noise in the rightmost image. But the prediction goes very wrong. Okay. The sports car become a toaster, right? And also you can make some noise in such a way that you can always predict a predefined class also. That is also possible. That's called a target learning. Again, this is another example where the model says this is ostrich. Okay. Again, school bus became ostrich just by adding a very mild perturbation. So, so these perturbations are not simply any noise. Okay, these are all crafted ones. Okay, crafted means I know the model, I used the model to create this particular noise, okay, to attack the model. Then once I have this noise, I can attack any model that you give to me. Okay. So this shows there is a remarkable gap between the human perception and the machine perception. Just a minute. So there is a huge gap between the perception of the human being and the machine, right? We never make such a mistake. These are all looks like a very, very stupid mistakes, right? We will never ever make. Okay? The brain is very quite fault tolerant. Okay, you can't attack by adding a very simple perturbation. So this shows there is a huge weakness in our deep models, right? Anyone who can hack into your deep model can easily attack these models. And all these things started with this particular work of Goodfellow, 2014, where he showed adding this perturbation to a simple panda image showed it made this as a given. And you can see the confidence, right? Initially, it was telling Panda as 60% confidence. When it is wrong, it says it's 100% confident. So that is another dangerous thing. The models are not only saying some wrong class, but very confidently it says the wrong class, right? So why these attacks are dangerous means I can always perturb the image, incoming image, to make the model say what I want to say, right? So assuming there are adversaries who can attack this autonomous driving vehicle, they can easily go ahead and do it. Okay, so they can make the school sign to read as though it is a speed limit or something like this. Another interesting thing is you don't even need that. You don't if you don't know what is your target system, right? So even then you can attack this kind of models because whatever model that is available to you, you train these attacks. That is, you generate the attacks from your own laboratory, your own models, and then use this attack, transfer this attack to any other model. Then also it attacks. This is called the transferability of adversarial attack. Okay, so the transfer rate is about 40 to 50% usually, which means half of the time I can attack the model, which is a very huge number. Right? That is what is depicted here. So you train, you get attack from your own model, this delta x, and then you can attack other model, third party model, very easily. So the model could be different, the data could be different, even then you can attack these models. So what we were talking about was imperceptible attack. So we are unable to see the noise after after adding it to the image, right? Now there is something called physical attack where the noise can be physical, kind of. I don't restrict the range of the noise that we are adding because initially I was telling 8 by 255 or epsilon, right? Now I'm opening up. Okay, you use the full range of my image, okay, and then attack the model. So this adversarial sticker that you are generating is something in a visible one. You can take the sticker and put it anywhere, right? And you can attack this model. So now the banana, if you put it near the banana, the accuracy becomes almost zero, whereas the what is it, toaster accuracy becomes almost 100%. Okay, so this sticker is actually meant for toaster sticker. You go and put anywhere the photo is there, you put this sticker there, it will always say as toaster. Okay, almost 90% of the time, right? We didn't even touch any other region of the image except this region. Okay, these are all same as the original image. Similarly, we also created adversarial frame here. Okay, so why to touch anywhere in the middle? We will put a frame around this image, right? So I give me some 5 rows and 5 columns around the image. Then I can add adversarial frame and then make your model fail. So this is what we call as adversarial frame. So you can see this is like, it looks like a photo frame. If you put this frame around this image, then automatically it will be used. So the dog became something like a maple, right? And this works across all the architectures. You give me 5 rows and columns of your image at the boundary, right? Then I can attack you more than 90% of the time. You will say a wrong answer. And similarly, there is a targeted attack. You can craft this adversary to say a specific class. For example, all this in the last row, all the frames are same. Even in the first row, all the frames are same. So this frame is meant for zebra class. Whenever you put this adversarial frame, whatever be the content of the image, independent of that, it is going to say zebra. This as 93% of the time. Okay. So similarly, in the first one, it will always say soccer ball for 95% of the time. So now you will wonder, so what happened to these deep models? There is so much, 95% of the pixels are untouched and clearly visible to us. I can see this very well without any perturbation. For these images also, the model fails miserably, right? So these are other examples from CMU where this is an interesting one where you can print the adversaries in your spectacle. Right? These are all paper spectacle where you can print the adversaries and then you will be recognized as a person below, right? So this is quite dangerous because many places we are using face recognition for access, right? If you wear the spectacle and then you can gain access as though you are somebody else, right? It's very dangerous. Similarly, you can put some stickers in the stop sign and then make this as a speed limit. Okay? Right. Now, it's not only that a classification problem is attackable, any problem, any deep model if you have, I can attack that. Okay? For example, this attack on the segmentation, you can see this image and this image, hardly any difference. You see there is some high frequency noise here inside, right? If you feed this bottom image, then you can see the output has changed drastically, right? All the people vanished from this frame, right? So which means if the autonomous vehicle is seeing this layout instead of this one, I don't know, it's going to be very bad even there, right? So now let us look at what are the attack settings that are available. So the adversary has no knowledge about the target model, that is one. It's called black box attack. Adversary has complete knowledge about the target model because you are having access even to the parameters. That is a white box. But if you have a partial information, then it is a gray box attack. So most of our work are driven towards white box attack because we always wanted to see worst case possibility, right? Any mission, computer related algorithms, we want to see the worst case accuracy, right? So that's why I will generate the model and give the model parameters to you, and you please assess the robustness of my model, how robust my model is. Okay, so that is a white box attack. And also adversarial robustness. When we started working in 2016-17, there were hardly 50 papers around at that, at that time, maybe. And this work became very popular, this area became very popular, and people started working. And now you can see there are more than 8,000 people as of today. So now let's get into how to get this attack. If you want to generate the attack, how can I do it? Right? Is there any questions? What do you think? So how to craft this adversarial attack, right? It's not so very difficult, right? So we know the last landscape, right? Whenever we train a deep model, we have the cost landscape, right? Basically, we do gradient descent and then reduce this cost or loss, whatever you call it. And when we reach the minima, and that is where your model is kind of settling down, and you are going to predict the incoming samples what is the class, right? So we will take an image actually, and we'll evaluate the image through the function. J is nothing but your deep model. Okay, you are feeding this image to your deep model, and then you are going to get a cast, the last output, right? And yeah, you are basically sitting at some particular location in a cast landscape. So this is shown just in 2D. Okay, but our last landscape in really high dimensional space. Okay, we can't visualize, so that's why we are doing here like this. So usually when we train, what we do actually we minimize the cost. Okay, dou j by dou w with respect to the parameters we wanted to minimize the cost, and we update the weights in such a way that the cost is getting minimized. Whereas in adversarial attack, the model is given to you. You are not going to touch the model parameters at all. Okay, because these are trained models already. So all you have to do is the model parameters are intact. Now we wanted to get the perturbation at the input space. What do you mean by that? Is how my cost J is getting affected by the value X, which I mean is each pixel of X affects my cost J. Okay, so that is what we wanted to find. So dou J by dou X. So dou J by dou X are, is nothing but another image which holds the gradient of the X. Gradient of this cost function with respect to the input, right? So this is what we call del X. Okay, okay. So dou J by dou X, right? For a specific class, right? Especially this is for the dog class, this is the true class, right? And this is the gradient that you get. So now to craft the perturbation, you should do something opposite to training. That means you should go along the gradient now and then get the perturbation. What you are doing here is once you have the gradient, make a sine function on top of this. You get plus one minus one and restrict the range to epsilon. Okay, so that's why epsilon is multiplied. So now this delta x contains values only between minus epsilon to plus epsilon. That's all. So what you are having at your hand delta x is called the adversarial perturbation. Okay, it's very simple to craft this adversarial perturbation, right? Once you have this delta x, now you go ahead and then add this delta x with x and then create x star, right? And this is what is called as the adversarial sample. So this is the adversarial perturbation. This is adversarial sample. Now, once you feed this adversarial sample to your model, it will most likely going to give you a wrong class. Okay. So this is how you generate the adversarial perturbation and then add it to an image and attack it. And this is a very simple way of creating this attack. So that's why it's called as a fast gradient sign method. Okay. Just one step attack. This is just on one step you are getting this gradient. Okay. Right. So there is the another work that I want to bring it to your attention. Now we are looking at okay, this adversary is actually for this particular image. So for every image, you can create this perturbation delta x. So it is an image dependent perturbation. Okay, right. So because we are taking the derivative of j with respect to x. X is the input, right? For each image, you will have different dou j by dou x, right? So for each image, you have to separately create this adversarial perturbation. Now somebody came and asked, why can I have one perturbation that can attack all the images, right? Can I make it image independent, data independent? So yes, there was a one work actually. It's called universal adversarial perturbation. Once you have this adversarial perturbation, you add this to any image coming from any class and then feed it to your model, then the model always gives you wrong output. Okay. So these perturbations are crafted for the given model. Okay. Independent of the images or classes. So now when we looked at this perturbation, they looked to stereo. How many such perturbations are there for this image, this models? Are there so many perturbations? If it is a single perturbation, then I can always go ahead and then fix this, right? So if somebody is attacking with this kind of a perturbation, then I can actually nullify this perturbation and make it uh, kind of, what is it, attack free, right? I can come out of the attack. So for that, we should know whether this pattern is fixed or there are varieties of pattern that can attack the same way. Right? So yeah, so one more thing about the fooling rate, what do you mean by this is the diagonal ones indicate the craft for this particular model and then attack, okay, attack this particular model. Craft for the particular model and attack some other model, okay. So this is called the white box attack, the diagonal one. The off diagonal ones are called the black box attack. So you are attacking some other model, unknown model, using this. So that's why I told it's about 40% attack rate you will get. Whereas if it's a white box attack, you will get more than 80% attack. One thing about this is, okay, training the perturb sum, this do not include the robustness for universal attack. So we were asking whether we can model the distribution of the adversaries. So yeah, we proposed a framework where you can generate the kind of a delta values here. Okay, this generator is like a GAN network, generator adversarial network, where the deltas are getting generated, and we wanted to have very diverse deltas. Okay, so that's why this diversity loss, the loss which we added along with the fooling loss, that helps us to generate universal adversarial samples that are very different from what is already proposed. Right? So you started getting varieties of perturbations that are coming out now because of the diversity loss that we include. I'm not going to go into this. Just I wanted to give you the overview what all you can do. So this is the UAP which was presented in the previous slide. Uh, So you can see these are all stereotyped one, right? There is hardly any difference. Whereas the what we proposed had varieties of perturbations. We can go from one perturbation to another perturbation, right? And basically you can walk from this is one perturbation, this is another perturbation. Linearly connect a line between Z1 and Z2, right? And walk along this line. All these perturbations in between are also kind of giving you the same fooling rate. They all are 87 to 88% fooling rate. Right? So which means, so you can generate so many perturbations for a given model. At the same time, you can move from one perturbation to another perturbation continuously and keep generating lots and lots of perturbations, which actually keeps the maintains the fooling rate. Now, then next difficult question that we asked, okay, we were all using data to train the model. So this the data. We already had Alexa data, so we were training using this Alexa data, right? Now, if data is not there, only model is there, how can you generate the perturbation? Okay. So that is what we asked. This is what we call as a data free. So which means the training data is not available. Only I am left with the model. Now how can I do this kind of attack? Okay. So then we thought of without data you can't even create the perturbation. So we need some kind of a data that has to be brought in. So then we thought of getting the data out of the deep model itself. Okay, so these deep models are trained with so much of data. Can I make the model to eject the data as output so that I can take this data and then use it for getting my adversarial automation, right? So what we did here is, so you can go to the CNN and then you can increase the specific class score in iterative fashion. Okay, you start with a random image here, and then you iteratively you increase the C value confidence. Right? Then automatically there is some kind of an image that forms in the image plane. Okay, and this is what we call as a class impressions. Okay, so these are all coming from the classes which learned, right? So these are the classes in which it learned, right? So we are taking out the data outside the scene, right? So even if you forget, sir, I forgot the class one, which I don't know what class I used. So maybe you can do this kind of a class impression and then see. Once you see this particular pattern, you will know what class that is. Okay. So now for each class, you can create the data like this, right? So they don't look natural, but many the structural things are intact. Okay. So then we use this data and then train the model in the same fashion as previous one. And yeah, we got a reasonable uh, white box attack. And the black box one actually improved from 40s to close to 50s now. Right. So now we are asking, okay, so this is a nice example for class impressions. By looking at this, you can immediately say what class is this, right? Any of you can you say what is the first one? What class it looks like? Yes,
Butterfly.
correct. Very good. What about the second one?
Dog.
Yeah, it's a dog class. Third is
Spider.
correct. Fourth,
Fish.
okay, it's called goldfish. Okay, so these are the classes from image. Okay, so yeah, there's one way you can see. Okay, you forget all the labels what you used. Now you first label if you want to see, I extract the class impression and then immediately you can see what class it is. Right. This is coming out of your model. So now we are asking, okay, so far we are using data, actual data or synthesized data. These class impressions are again data, right? Because I have to feed and then generate that result. Right? Now we are going one step further and then asking, can we just get rid of the data? Without data, can we craft the perturbation at all? So there is no dependency on the data itself, which means there is no dependency on the input and output, right? Data is nothing but input, right? If I don't have input, then I don't even have output because they are coming as a tuple, right? So then it is kind of it leads to a scenario where it is independent of the task. Whatever be you give, whatever you get, I don't care. I can attack the core of the CNN, okay, without even looking at the applications. Let it be a classification model, segmentation model, or whatever model it be, we can attack this model because I don't want any data. right? Without data, I can do that. So there was a proposal which was published in PAMI 19. So what we did here is, so all you have is the CNN layers, okay? So all what you can do here is, okay, the discriminative properties are embedded in the CNN layers, okay? Can I go and corrupt them, basically? So basically what we did is, for each layer we found the activation value and then we maximize this activation value, right? That's all we did. So the core of the net is whether it's classification or segmentation or depth estimation, whatever it is the same framework, okay, where you are increasing the activation of the layer network. So with this simple loss function, you can basically attack all applications, mission applications. So we are almost you know, 5 10 minutes. I will briefly take you through how to defend our model. At the end of the day, I want my model to be robust. Okay. So I will skip all these things and go here. And see, all you are going to do is, one way is input pre-processing. Sir, wow, the adversary is embedded in the image. So I will do some kind of a pre-processing on the image and then remove the adversary and feed it to my model. So that's a valid one. Okay, you can do various quantization, JPEG compression, whatever you want. You do blur the image or whatever it is, but they don't work actually, right? So you can't get adversarial robustness just by doing the pre-processing. Okay. So what actually works is the adversarial training. What is the adversarial training is? It's very simple. So all you have to do is you just train the model, right? So now you generate the adversaries, okay, which means maximizing the loss. You are generating the adversarial perturbation. Now add this adversarial perturbation to an original image, right? And these perturbed images, or you use these perturbed images and then train your model. Yeah, that's all. As simple as that. So first you generate the perturbation for each of the images, right? Add that to original image and then train. So you are going to train your model with adversarial samples, right? That's all. So once you train with adversarial samples, then it knows, oh, this is an adversary guy, we should classify like this. So this is the adversarial training that we are talking about. And there are two types of adversarial training. One is single-step adversarial training, other one is multi-step, adversarial defense, multi-step adversarial defense. But the single-step defenses are okay, low computational cost. I'm happy with that, but it is susceptible to a bigger attack, basically, right? So these single-step adversarial attacks are susceptible to gradient masking, right? Which means it is easily attackable by a stronger attack. Whereas multi-step defense, you create the attack using multiple steps, which is the strongest attack actually. When you use multiple steps, generate this adversarial sample, then that is going to have huge, uh, it's going to be a very good attack actually. So to create a robust model, all we need is very good adversarial perturbation, right? Not the weaker one. So once you have the good adversarial perturbation, then you can train with this adversarial perturbation and then make your model robust. And also, if you look at this cost surface, usually the robust model, the PGD is a robust model, it shows a very nice cost surface. Whereas FGSM, the single step one, cost surface is quite rough, sharp minimas are there. Okay. Right. So FGSM adversarial training is this. So all you are going to do is take the samples, take the adversaries of all the M samples, and then train your query. So I'm not going to show you any original sample. Only adversarial samples will go. See, you will show to the model and then train. Now, one question we are asking whether we can train a robust model using single step training itself, right? Because they fail miserably, that's why we are going for multiple step. If single step adversarial attack can be made to work like multi-step attack, then that will be great. It saves a lot of cost, right? Otherwise, I will, if normal adversarial training is 10 to 12 times more load compared to normal training. Yeah. So there is a simple observation what we did. Okay. There is FGSM adversarial training. There is something called RFGSM. The difference between FGSM and RFGSM is you directly get this perturbation from the image. Here RFGSM you get the perturbation after adding some noise. That's all. So you express some amount of Russian noise you're adding. That's all. And after that you get the FGSM. So RFGSM is this R comes because of this addition of random noise before FGSM. That's all. But there is no big difference between these two perturbations otherwise. So a common sense says these two attacks should behave in a similar way, right? So whether you are doing FGSM or RFGSM, your model should behave in the same way. So and what we are doing here is we are verifying that. If you look at this PGD adversarial training, yeah, these two models and the PGD they look similar. Okay. So which means the error is very, very minimal, close to zero. Yeah. Across all the iterations, 0 to 300, 50, right? So 3,000, 60,000, right? So 6,000 iterations. Whereas, if you look at the FGSM adversarial training, this FGSM and RF, they are close only up to some 25 epochs. After that, the what is it? So the gap between this FGSM and RF actually shoots up very well. So 400, 300, 400, it always stayed around 1K. So this shows that there is a kind of a overfitting that is happening here. Some kind of a problem is happening here, right? So now our objective is how to make this FGSM to work like this PG. Okay. So it's a very easy fix actually. So FGSM and RFGSM should be close to each other. That's all. You just put this as a regularizer in your model. FGSM and RFGSM, right? Should be close to each other. So all we did is the regularization here, right? So you have the FGSM logic should be as close as to RFGSM logic. That's all. You add this to the main class function and you train your model, and what you are going to get is a robust model. Okay. So now we can look at this. This is the 47.51 is the original PGD training, which is typically 10 to 20x costlier than normal training. Whereas the proposed one gives very close to this 47, 46 point something. And also it's the clean accuracy is slightly better than even the PGD one, right? So we got almost a similar performance of the PGD with one step. We didn't do with 10 steps or 20 steps, one step. With one step, we are able to come very close to the state of the art accuracy. Also, if you look at the time, training time, right? So adversarial training, you can see the proposed one takes much less time compared to other ones. It's PGD adversarial training. So basically, you can say uh, equivalent to 2 times the single step adversarial training. So that is because you have to generate FGSM and RFGSM. For each you need one forward pass, right? So that's why 2 times it is costly. So 2x is nothing, it's very simple. 10x, 20x is really bad. So now I think we have only 5 minutes left, okay? Maybe I will quickly cover this one and then stop here. Now we are asking whether we can get some kind of robustness without any adversarial training at all, normal training itself, whether it can. So this is again a simple fix here. So what we observed here is the same thing. We were looking at the loss of adversarial loss should be always higher than the clean loss, right? If this is not happening, there is something wrong with that model. So when we plot this loss ratio, we expect this loss to be more than 1. So initially for few iterations it was more. After that it fell below. It's around 0.2, 0.3. Whereas if you look at that validation loss, you can see at this particular point there is overfitting that is happening because the training loss is coming down, whereas the adversarial loss is going up. So then we thought of, okay, there is something happening here, some mysterious phenomenon. So how to avoid this particular region, okay, and then escape this region while training. So then the dropout is one thing that came handy, right? So dropout means you are basically drop out 0.5 means you drop 50% of the neuron while training, right? And which means half of the neurons randomly won't participate in the training process, which means you are learning less during that time. Okay, so we thought of deploying very heavy dropout during this particular critical phase, so that it is not learning much during this particular critical time, and then slowly you taper down the dropout and then make it 0 just halfway through your training. Right? So that's all. This is called dropout scheduling, right? So this is what we did actually. So we added the dropout even with the 2D conv layers as well as the fully connected layer. And then starting you had the maximum dropout. Okay. As the training progresses, we just bring down this loss value, right? And then make it 0 at some middle point. So if there are, you're doing for 100 epoch training, you start with 90% dropout in the first epoch, and then keep to slow come down, and then make this dropout 0 at 50th epoch. That's it. It's a very simple trick just to avoid that vulnerable region. Then it automatically worked. So this is one single again single step attack, but it performs on par with the multi-step attack. So PAT is PGT adversarial training, which is multiple step model. This is 10x costlier, whereas this is just 1x. So the gap is about 1.5%. But if you look at this, what is this 47 and 45 we are talking about is, this is called the adversarial robustness. If I use 100 adversarial samples, only 47 samples I will say correctly. 45 samples I will say correctly. Remaining 55 samples I am going to predict wrongly. And this is the situation now, even for the smaller data set like CIFAR, right? But this is something is better than nothing. That's what we are having here. instead of having 0% zero accuracy for our robust adversarial samples, we are having somewhat 45% accuracy. If our models are getting bigger, if your data set is getting bigger, then this adversarial robustness goes much more down. So for ImageNet, you get something very close to 15% or 10% only, right? Adversarial robustness. So there is a long way to go, and we are very far from achieving this goal. Okay, it is not even deployable friendly at this point of time. So, and one more phenomena that you can notice here is whenever you do make your model robust, you have to sacrifice clean accuracy. So 95% accuracy has come down to 85%. Same thing happens even here, 82%. So you have to pay in terms of clean accuracy to gain some robustness. Okay. And the robust accuracy is also around 50% only, even for the state of the art adversarial training. So this shows the models, that the deep models as of today are easily attackable and very hard for us to defend these models. Making the robust model is at a reasonable cost seems to be a much, much bigger challenge. So, and this needs to be addressed because we'll never know, because the attacker can come at any time and then attack the system. It's better to prepare now itself for these things. So with this, maybe I will stop here and then maybe take some questions.
If anybody has any question, they can ask to sir.
Sir, I have a question.
Yeah.
So for instance, in one of the slides you said we have to generate the adversaries and then train the model along with the clean samples. So is there an upper limit on generating the number of such strong adversarial samples?
See, actually, in the actual adversarial training, initially they were doing only the adversarial samples are used for training. Not even, we don't even mix the clean sample. So we always use adversarial samples. Every iteration you have to create the adversarial sample and use that for training. Okay, every iteration you should do.
So that is generated on the fly, is it?
On the fly, yes. It
Okay,
is not
highly randomized.
No, for wherever the model is, you want to generate the adversary for the current model state, right?
I see. Okay.
Right. And this adversary generation is expensive because PGD adversarial generation, because you want to generate the stronger adversary, right? That comes only through multi-step adversarial, right? So you have to spend at least 10 times, you have to do a background, 10 or 15 times, depending upon the PGD attack that you want to use. So you have to do 10 times back propagation and then get the adversary. So once you get the adversary, now you go ahead and then train. Once you train them, this thing for next iteration, again you should create the adversary using 10 steps, 10 times your back propagation, right? So that's why I told the training cost becomes 10x when you use multiple multi-step adversary training.
Okay, thank you.
Sir, I have one question. Should
Yes.
I go ahead?
Yeah, sure.
Thanks for this nice session, sir. In one of your slide, you come up with the concept of data-free model. So how are we taking care of high while using the data-free model? There not being the test data of issue of underfitting or high variance.
So in adversarial training, we are all looking at the models which are pre-trained, right? Already trained these models, right? We are not going to train these models, right? At least when we want to attack the model, right? So how to attack? See, for example, if you are training your model, right? And you are giving me the model and asking me to attack, okay? So, but to attack that, again, I need your data to create the attack, right? But you can say this data is proprietary data, I cannot give. Okay, it cannot come out of my house. Now, how will you go ahead and then create a data? So that's what we are looking at, right? Even without data, how can I attack your model without the training data? So this is kind of more of a practical setup that we are looking at. Why we should assume that data is available for crafting that attack, right? So you go to any industry, they one thing they will never want to share is the data, because that data is their proprietary thing. They just don't want to leak out anymore. Okay, model they are ready to give you after training. Okay, do something with the model. Okay, now if I want to assess how robust the model is, I cannot ask the data, right? So I have to use whatever I have. But that's why we went ahead and then did something along that line to make it more practical.
Thank you, sir.
Is there anyone else who want to ask a question?
Excuse me, sir. Devmalla here.
Yeah.
Yeah. So, sir, how we can? So, can you just please go to the slide where we discuss the approach we are following to get rid of this? I mean, to tackle this attack.
Which slide are you talking about?
Where we are generating along with the I mean original images after we finish training, then we are adding a few I mean adversarial noises, and then again the algorithm part.
Oh, this one is it.
Maybe later. So actually, I mean, how is this? Suppose so the yeah. So for our this purpose, the I mean noise examples that are getting generated. These are I mean how these noise examples are getting generated is I mean independent of anything, right?
No, this is dependent on the image now, right? So here we are doing with respect to the X, right?
Mm-hmm.
So in the next one we are telling, yeah, independent also we can do, right? So you need to have the cost without the with respect to X, it is not there. So that I didn't cover much, but yeah, this is the one where you have the loss, right? You are maximizing the layer activation. That's all. Have a random image somewhere here. You maximize the activation across all the layers of this network. Then automatically you get some kind of perturbation at the other end. Okay. So these are the perturbations that you get each of this. Right.
Okay.
So
So
there is no data involved in this, just only one class. And you are just maximizing this activation. That's all. So what you do is initially you will give the random image, and then when you try to maximize, automatically the random image becomes some patterns like this. These are the adversarial images.
okay, so I understood.
We have a question in the chat from Avinash. How to frame an attack so that the classifier always gives a particular class output?
Okay, so we are always moving against the training direction, right? So in this, okay. So basically you are moving, increasing the gradient, right? Instead of that, you are going to minimize the So instead of true class, you will be doing minimizing for the false class. That's all. So here you are seeing, right, the y true, right? Okay. So you minimize the cost for the targeted label. That's all. As simple as that. Here you are maximizing the cost for the true class. There you will be minimizing the cost for the wrong class. That's all. You have to do a minimization with respect to this wrong class. So if you do that, then it will automatically try to say that class instead of some other class. So that is what is called as a Targeted attack.
Okay. So, okay, so no more questions. Yes. So thank you, sir, for your insightful and informative talk. I'm sure each one of us might have learned something new today.
Yeah,
Your
I'll be happy. Yeah.
yes, sir.
Okay.
And
Right.
your expertise and passion for the subject matters truly shine through, and the knowledge that I gained from reading your work undoubtedly influenced my research.
Sure.
Thank you for taking the time to share your knowledge through this remarkable and enriching talk. Hope we could connect in future as well.
Sure. Thanks, brother. Thanks.
Yes,
Thanks a lot.
and thank you everyone for joining.
Thank you. Thank you.
Thank you, sir.
Thank you, sir.
Thanks.
Thank you, everyone. We are closing the session.